Swayam Prabha. Digital India. Educated India.
Till now we considered various kind of analysis in the rotor system. Mainly we considered transverse and torsional analysis for free vibration, forced vibration and instability analysis. In these analysis mainly this can be done at this design stage, and if there is any problem in the machine regarding the resonance, if it is falling within the operating range or if operating range is within the instability regions, we can do design modifications and we can able to rectify these kind of problems. So, whatever the analysis we have done is very useful at design stage, and once we have designed the rotor concerning all the aspect of the resonance and critical speed or instability reasons, but in most of the practical case when we fabricate the rotor or machinery and when we assemble them and when we operate it, we found that there are some inherent difficulty which we face in such machinery. These difficulties are in the form of some kind of inherent fault which comes into the system, maybe because of maybe manufacturing process or during assembly, if proper the procedure is not followed, and because of this the rotor may not behave as we expect or as we have designed. And in such cases, because we cannot able to now modify such a machinery because we already manufactured it and we assembled it. So, the procedures to rectify this kind of faults or the problems in the machinery now we will take up in the subsequent lecture. And we will see that in machinery, not only at the stage of commissioning of the machine, a new machine, but during operation various kind of wear and tear of rotating parts and the stationary parts take place, and because of that whatever we achieved in the design stage, that particular performance this machinery may not give. So, during operation and when we are making measure overall in this machinery, we need to take care of this kind of fault which comes into the system inherently, and we try to remove them. So, in today's lecture we will take up a very specific fault which is very common in such rotating machinery, that is unbalance, which will always be there in the rotating machinery, and based on the various methods available, we try to balance the rotor up to the extent possible, and that will depend upon type of machine which we are trying to balance. And so, these aspect will be dealing with in the present lecture. The overview of the lecture is that rigid rotor balancing basically will be focusing in today's lecture, but overall concept of the static and dynamic balancing will be giving. Apart from this, the rigid rotor, flexible rotor basic concept will be introducing in this particular lecture, and the off field balancing or on field balancing, especially for rigid rotor, we will try to cover in this particular lecture. Now, various kind of the fault which the rotor system can have either at the stage of commissioning the rotor or during the subsequent overhaul. So, the most common, as I discussed, is the unbalance, and apart from this the second most critical is the misalignment, which can generally occur between two shafts when they are connected by a coupling or at the bearing when a single shaft is mounted on two bearings, then we may have misalignment between the shaft and the bearing bore. Apart from that, we can have rotor stator rubs, bent or bowed shafts, fatigue cracks onto the shaft, the wear and tear of various moving and stationary component of the rotor and stator, loose components, fault related to components of bearings, gears, couplings, blades, seals, electrical motor, etc. So, we can able to see that various fault which may come, which we cannot able to handle at the design stage. This automatically comes into the system if we do not take care of the proper maintenance or the proper procedure of assembly of the system. And we will focus on the unbalance, and we in the inherent unbalance we call that as a residual unbalance. So, this is the most common fault amongst the various kind of faults, and it occurs because of variety of reasons like manufacturing error, fits and tolerances which we give in various machine components. We may have material inhomogeneity, improper commissioning of machines, thermal deformation of shaft, wear and tear during operation, residual stresses, and so on. So many reasons because of this residual unbalance may come into the system. Now, once we found that there is a severe level of unbalance, then we need to balance this particular rotor, and there are different balancing methods are available. So, like static and dynamic balancing of rotor, these methods will depend upon the type of rotor, the application, the geometry of the rotor, various other parameters which will govern which type of balancing we should be doing. So, at present I will be introducing this terminology, but subsequently we will be dealing with these methods in more detail. So, the static and dynamic balancing of rotor. So, in static balancing generally we do not rotate the rotor at a operating speed, but at stationary rotor we try to see the condition of that and try to balance the rotor. In dynamic balancing, as the name implies, we need to rotate the rotor at certain RPM, so that the effect of unbalance comes into the rotor in the form of centrifugal force, and that will give the idea about the balance condition of the rotor, and based on that we can able to balance the rotor. And in the rotor itself we have two class of balancing, that is rigid rotor and flexible rotor balancing, or sometime it is called slow rotor or slow speed or high speed rotor balancing. As name implies, we will be explaining this particular what is the rigid rotor and flexible rotor and what is the difference between them in more detail subsequently. But in general, if rotor is rotating at slow speed, we do slow rigid balancing, and at high speed, especially near critical speed or above critical speed, then we do the flexible rotor balancing. Various basic principles of the rigid and flexible rotor balancing are there, and in these two balancing procedures basically we will see that there is a fundamental difference between these two type of balancing that we will see subsequently. But for rigid rotor there are two basic methods. One is conventional cradle balancing machines, and in this we have dedicated machine for balancing. We need to take out the rotor from the machine, actual machine, and then we need to put on the balancing machine, and there we can able to find the condition of the balancing of the machine. And sometimes this is called off-site or off-field balancing, because of we need to take out the rotor from the actual machine for balancing. There is another method, that is modern influence coefficient method. that is we can able to do balancing with this online or on-site balancing or field balancing. Sometimes we refer to this particular method. These methods will be dealing with in more detail in the subsequent of this lecture. In the flexible rotor balancing, again there are two basic methods. One is the modal balancing method. In this we try to balance the rotor for various modes, first mode, second mode, third mode, like that. In the second method, influence coefficient method. In this this is more advanced method, in which the concept of the influence coefficient for rigid rotor balancing will be extended for the flexible rotor. In this, the influence coefficient will depend upon the speed of the rotor, because we are operating at the flexible mode. So, we will see that the influence coefficient will depend upon speed, and this method is more advanced as compared to the modal balancing method, in which that is more difficult, basically modal balancing method, but influence coefficient is relatively easy. When we are talking about the balancing, then the question arises, how many number of balancing plane we should have to balance a rotor. Conventionally, we know that for rigid rotor we require two balancing plane, because we need to balance the force as well as the moment. So, in general, for rigid and long rotor it can be balanced by two balancing planes, but when we are coming to the flexible rotor, then we need to balance by n balancing plane, where n is the number of flexible mode we need to balance. That means, if we are operating the flexible rotor above third critical speed, then that many planes, that 3 planes will be required to balance such a flexible rotor. And sometimes not only we balance when we are balancing the flexible rotor, so often it is suggested that not only we should balance the flexible mode, but also the rigid mode. So, that means, for flexible mode, if we are balancing up to nth mode, we require n plane, but what about the rigid body mode, that is the rigid rotor case. So, the total number of balancing plane will be summation of this, and that means n plus 2 balancing plane will be required to balance this. So, 2 planes will be required at slow speed and n plane at the high speed. So, total n plus 2 balancing plane will be required to balance a flexible rotor in whole range of the operating speed. So, this is the concept of the rigid and flexible mode of rotor bearing system. So, you can able to see the solid line is one position of the shaft, and maybe other extremities coming here. So, this is a rigid body translational mode, and this is the rigid body conical world mode. So, in this, because these two are the rigid body mode, when we are operating the rotor at low speed, we require when we want to balance these two modes, we require 2 planes. When we are coming to the flexible mode, so this is for simply supported rotor, let us say, we have this is the first flexible mode, half sine. To balance this, obviously, if we apply a force in this direction, so when we apply force, what is happening? When we apply force like this, let us say in the form of some unbalanced force, so we will see that we can able to decrease this particular amplitude of vibration. So, in this, if you want to balance the first mode, the single plane is enough to balance this, but when we are coming to the second mode, in this you can able to see this is a full sine wave, and to balance this we require 2 forces here to balance this, because this will diminish the amplitude of here and here. So, up to second mode we require 2 flexible 2 planes to balance. So, this is the basic principle of the flexible mode and the rigid mode balancing. Now we have seen basic methods of balancing, what are the type of balancing, and especially the rigid rotor and flexible rotor balancing. Now we will go in more detail, especially theoretically the basic principle how we can able to balance a rotor with especially we will focus first for the rigid rotor case, in which we will be focusing on the that is static balancing and dynamic balancing. So, basic principle based on which we this balancing procedures are based, that we will try to highlight. So, for let us say unbalance in a single plane. So, in this particular case, if we have a rotor like this, so let us say is supported for a single plane, if we want to do balancing. So, basically it depends upon the geometry of the rotor. So, for this rotor system, you can able to see if it is mounted on some kind of bearing at ends. So, as such the mass of the shaft is negligible, is flexible, the disc is heavy, and we can able to see that this particular the dark, that is representing that the center of gravity is there. It has been exaggerated here just to show that how the center of gravity can give unbalanced force. Generally, this eccentricity from O to G will be of the order of microns in actual rotors. So, in this particular case, because of the geometry of the rotor, we can able to see that we can able to balance this particular rotor by single plane itself, because most of the unbalance is there in this plane itself. In two plane balancing, so basically in this you can see that there is a long rotor, and in this is flexible shaft. In this particular case, this long rotor is offset such that the eccentricity is parallel. So, basically this eccentricity is, so this is offset in transverse direction, and the eccentricity is constant throughout. So, this particular rotor we can able to if we want this effect of the force, centrifugal force, basically it will be acting at a middle, and we can able to balance this particular rotor using single plane. That means we can able to balance with the static unbalance itself, because once we are doing the balancing in this single plane, the static balancing method is applicable. But the same long rotor, if the center of gravity is there at the bearing axis, but it is having some tilting by some amount, then we will see that when it is this rotor is rotating, there will be some force which will form a couple, and this particular couple will give two forces and two different planes. So, obviously, we need to balance this particular rotor by two planes. So, single plane balancing will not be enough in this, and when the center of gravity is at the center, the pure couple will act, and that is why we call this as the couple unbalance. If we have a combination of this offset of the disc and like this and the tilting, then that particular unbalance is called dynamic unbalance. So, we will see these three cases subsequently. This is another category of the rotor in which the rotor is very thick, flexible, and in this particular case this dotted line is basically the center of gravity variation. So, if we take a particular slice in between, we will see that center of gravity is here, but center of rotation is here. So, and this is eccentricity in the radial direction, and if we take different slices, we will see that the position of the center of gravity, not only the orientation, but also the radial position will change. This also we have exaggerated here. Generally, this eccentricity will be of order of microns in the actual rotors. Now, coming to the principle of rigid rotor balancing. So, for single plane balancing, as we discussed earlier, This we can able to balance by a single mass if we keep opposite to this particular this unbalance. So, if because of the actual unbalance which is m e, and the force, unbalanced force will be omega square. If we multiply, that will be the force. So, this is the unbalanced force because of a eccentric mass. So, rotor center of gravity is offset by some amount. So, OG is basically is the eccentricity. As I told, this distance will be very small, and this is giving a centrifugal force of this amount. So, if we want to correct this unbalance of the rotor, we need to put some correction mass mc and at a radius, let us say r. So, this particular mass which we are keeping somewhere opposite to this here will produce a force mc omega square r that will be acting opposite to this, fc in this direction and f is acting in this direction. So, these two forces, if they are equal, then this unbalance can be balanced. So, this mc is basically correction mass, and we are keeping at a relatively larger radius. Correction mass will be smaller as compared to the rotor mass. That is why we need to keep at a larger radius. Here rotor mass will be relatively higher, but this eccentricity will be relatively smaller. So, if we equate these two forces, we will see that the correction mass will be given by this expression. So, by this we can able to obtain what should be the correction mass in a single plane balancing, which we call it as a static balancing, because in this particular case as such we need not rotate the rotor at high speed. Now, we will see the static balancing, two plane balancing. So, there is a rotor, in this there is offset of the rotor. So, center of gravity is offset, but there is no tilting of this particular rigid rotor is there, and because of this is giving this centrifugal force m e omega square. Let us say that particular force is F. Now, to balance this particular unbalanced force, if we are keeping two masses here in these two planes, because generally we will be having provision to put mass at the sides of the rotor. So, here we are keeping a mass m1 at radius r1 and here m2 at radius r2. So, they will give force F1 and F2, and obviously if we want to balancing of this force F1 plus F2 should be equal to total force. So, here you can able to see this F is the force of the unbalance, and these are the correction masses force, centrifugal force. So, F should be F1 plus F2, and apart from this whatever the additional mass which we are keeping M1 and M2, they should not produce additional couple. So, to make sure that if we take the moment about, let us say at this point, this will not contribute to that moment, but the F1 and F2 moment should be balanced. So, if we are satisfying first condition and second condition, and from this if we are obtaining what should be the F1 and F2, then we can able to balance this static unbalance using two planes. So, here we are balancing with two plane, but actually this particular unbalance in the system is the static unbalance. So, from these two equations we can able to solve the F1 and F2, what is the correction mass required in plane 1 and 2. In this particular case, even the rotor was long, but because the eccentricity was symmetrically present in the system, so the system was having static unbalance. Now, in practical machine, the position of the correction masses are determined from the shape of the rotor. In practice, the removing some part is done by drilling, milling or grinding of the rotor. If we want to add some weight instead of removing the material, we require the use of wire shoulders or bolted or riveted washers or welded weights. So, this is the practical way of adding or removing the mass from the actual machine. Now, couple and balance, in which the center of gravity of the rotor is at the rotating axis, but the rotor is tilted by some amount, by some angle. So, this will give a couple which will be equal to I d minus I p, this angle, tilting angle, and omega square. Basically, I d is the diametral mass moment of inertia of the rotor, I p is the polar mass moment of inertia of the rotor, omega is the spin speed of the rotor, and phi is the tilting angle of the rotor. So, when because of this tilting, there is a couple acting. To balance this couple, we require masses in two planes, and in this particular case, because we need to make a couple, we need to keep these masses in the opposite faces of this particular rotor, and they will give P1 and P2 force like this. So, this is the unbalanced couple, and we are correcting this couple by two masses M1 and M2. So, they are giving P1 and P2 force. So, we should have this condition that the couple produced by these two forces should be equal to the unbalanced couple, and these two forces should also balance, because they should not give additional force into the system. So, these two forces should be balanced. So, from these two equation, we can able to get the P1 and P2, the correction mass and centrifugal force, and for plane 1 and 2, or like this. So, you can able to see that these two forces should be equal also, because they should produce couple, but they should balance each other. Now, when we are talking about the dynamic unbalance, in which case we have not only the offset of the center of gravity from center of rotation of the or the axis of rotation of the bearing, but tilting is also there. And in this particular case, the offset of this particular center of gravity and the tilting, these two plane may be different. This point will be more clear here. So, because of the offset, let us say we have a centrifugal force F. This particular F is, let us say, in a vertical plane, and the couple which are coming because of the tilting is, let us say, in another plane which is inclined with the previous plane by beta angle. So, this couple is acting on this inclined plane. Now, we can able to see that we need to balance this particular force as well as the moment. For this, what we can do, we can take one at a time. So, to balance the force, if we have two correction planes 1 and 2, if these are the correction plane. So, what is the correction force required to balance F in plane 1? Let us say that comes F1, and in plane 2, let us come it comes F2, and because we already seen how we can able to get the F1 and F2 if we want to balance a single centrifugal force. So, those two relations will be valid here, and based on that we can able to obtain the F1 and F2 to balance the F. Then, if you want to balance the moment or the couple, we need to apply P1 and P2 on this plane, such that they should produce a couple equal to this, and they should not add additional forces, as we discussed in the couple balancing case. So, now you can able to see that in this particular plane we have F1 and P1 to balance these two force and couple which are in different plane. Similarly, here we have F2 and P2 to balance these two couple and force which are in different plane. Now, to balance the whole system, obviously we need to find the resultant of these two. So, this is the resultant R1, which is the resultant of P1 and F1, and resultant R2, which is resultant of F2 and P2. So, these will be the correction forces in plane 1 and 2, and you can able to see their directions are now different because of the presence of the centrifugal force and the couple unbalance in a different plane. So, that is why this result in R1 and R2 will be at different angle and different magnitude, which we need to keep in these two balancing plane. So, this was the basic principle of the rigid rotor balancing of the static and dynamic balancing. Now, let us define the unbalance more precisely. So, in previous slides we have seen that generally we are balancing a centrifugal force due to the residual unbalance and by some correction mass, so which we are keeping at a certain radius. Now, you can able to see that omega square is common here. So, that will go out because both the unbalance and the correction mass are rotating at the same speed. So, basically we will get this equation. So, this product is important, mass into eccentricity or the correction mass into the radial position is important, and this is called unbalance vector. So, this is unbalance vector, and magnitude of this unbalance vector u is m e, which sometimes we call it as unbalance. So, the product of mass into acceleration, the magnitude of this unbalance vector, the product which is product of mass of the rotor into eccentricity, is we call it as a unbalance. So, just unbalance, if we are saying, there is nothing but the mass into the eccentricity of the rotor. Now, the question comes, if you want to balance this rotor, so up to what extent, again I am starting this slide. Finally, we want to know up to what extent we should balance the rotor. There is a question we always think of, whether, because we know that practically is not possible to balance the rotor perfectly, and some residual unbalance will be left in the rotor. So, this question is very pertinent, that up to what level we should go for balancing of the rotor. So, the smaller the unbalance, the residual unbalance attained in the is the better. So, best is if we can reduce the unbalance of very small, then is better, but however in practice and practical application we must take into account the time and expenses necessary to balance the rotor. That is very important in industry. Therefore, it is appropriate to vary the permissibility of unbalance depending upon the kind of rotating machinery. So, kind of rotating machinery governs what kind of hang. So, we are defining a term balance quality, which is epsilon into omega, where epsilon is a correction plane eccentricity, omega is the maximum angular velocity in the operating range of the rotor. If we are talking about the single plane balancing, then this correction plane eccentricity for static case will be given as static unbalance divided by mass of the rotor. If you are talking about two plane balancing, either static or dynamic, then we will be defining two parameter, epsilon 1, which will be u1 by m by 2, this is half of the mass of the rotor. So, this is the unbalance in one of the plane, and epsilon 2 in unbalance in the second plane divided by mass of the half of the mass of the rotor. And in this case, whichever the larger value will be the quality of the balance quality of the rotor will be. If we now, if the balancing quality of two rotors are equal, the load transmitted to the bearing are same, even if the dimension of the rotating machines are different. So, you can able to see that with the balance quality, we can able to compare two different rotors, because finally, whatever the unbalanced forces are there, that is transmitted to the bearing. And if these two the balance quantity of the rotor are same, they will produce the same force at the bearing. The permissibility of the unbalance is given by international standardization organization like ISO or various national standards. For example, balance quality defined by the Bureau of Indian Standard BIS is given as balance quality is equal to epsilon into omega, the same as the previous one. Only thing is unit to be noted, epsilon is in millimeter and omega is in the radians per second. Various balance quality is classified these are several grades are there. So, G 0.4, G1, G 2.5, like that we can go up to G 4000. For example, G 100 is G 100 means that the maximum permissible value of balance quality for this grade is 100 millimeter per second. Based on experience, the specific balance quality grade is recommended for individual rotating machinery. For example, G 0.4 is recommended for gyroscopes which are requiring very high precision, G 2.5 for gas and steam turbines, G 40 for car wheels or rims, G 4000 is for marine for G 4000 for marine engines, in which a lot of vibrations we can able to tolerate, and we can able to refer to various standard. This is one of them. Apart from that, these are the various standards available for balancing, which have been updated over a period of time also. Now, we will see how a practical rotor can be balanced and what are the type of methods and what are the type of machines available and basic principle of those methods to balance a practical rotor. In this we have two type of machines. One is shaft support machine. The resonance frequency of rotor system is low because the support is soft and the rotor runs at a speed above the resonance of the support system. In this particular case, generally we measure the vibration amplitude and then we convert that into the force. There are other system in which hard support systems are there. In this, the support natural frequencies are relatively high and they measure the rotor unbalanced force directly, independent of the rotor mass and the configuration. So, depending upon the geometry of the rigid rotor, a single plane or two plane balancing method are employed. So, basically the single plane or two plane balancing, especially for the rigid rotor, it depends upon the geometry of the rotor, and in the present lecture both will discuss the single plane and the two plane balancing. So, for single plane balancing, if a rotor is so for single plane balancing, if we have a rotor like this is the center of rotation of the rotor. If it is having eccentricity, large eccentricity, let us say is here. If we mount this particular rotor on some frictionless support, let us say if we mount this on frictionless support, and if we rotate this rotor by hand by some amount and we allow it to because of the friction, after some time it will stop. So, we expect that because of the unbalance, if unbalance is heavy, it will try to stop in this particular position. If we again rotate this, maybe it will come and rest in this particular configuration. This will indicate that there is a some kind of unbalance in the rotor which is somewhere here. To balance this, obviously we need to keep some kind of correction mass in other side, and if we are putting this arbitrary some value, and if once we have put it, if we are again rotating this, if it comes again in the same configuration after once it stops, that means whatever the correction mass we kept is not sufficient. We need to add some more mass in that particular part. Again we need to give a rotation by hand and see how it stops. If it stops something like this, that means whatever the additional mass we kept is very heavy, and because of this is coming in this position. So, we need to remove some mass from here, and if we have removed some mass and if again we are rotating it, if the rotor is stopping at some indifferent position, if once we rotated is coming here, second time if it is coming like this or any other position. So, all the time when we are rotating this rotor, whatever the marks are there, they are coming at indifferent position all the time. That means now the rotor is balanced. So, basically we need to see this particular path. So, like this we can able to do the static balancing, and most of the rotor in which the most of the mass of the rotor is at one plane, they can be balanced using this procedure, like propeller in the aircraft, they can be balanced like this, in which most of the mass is situated in a single plane. Now, we will see how we can able to balance a rotor in which the balancing is there required for the two plane balancing. So, you can able to see this is a two plane balancing machine, which we call it as a cradle balancing machine. In this this upper part is the rotor, which is mounted on one support. This is the some kind of bearing support, which is frictionless support to the rotor, and this whole assembly of the bearing and the base is mounted on some kind of flexible support, and this is the rigid base. This flexible support, if we see from the side, is something like this. So, is mounted on basically 4 flexible springs, and this is the rotor and this is the bearing. This is the bearing block, this one. Now, in this there is a provision to fulcrum or pivot this particular frame either at F1 location or F2 location, which is just below this plane and this plane. Basically, in the real rotor, we can able to add on balance here or here. So, these are the balancing plane 1 and 2 for this rotor, and just below that we have provision to fulcrum this this whole frame at this point or this point. So, if we are fulcruming at this point, you can able to see that we will be having motion. So, we will be having motion of this about this F1. So, whole assembly can rotate about this point, because we have fulcrum like this F1, and once we are fulcruming like this, that means what is the correction mass required for balancing the rotor in second plane, we can able to obtain using this. In the second case, if you are fulcruming here at F2, then the whole assembly when we are fulcruming at F2, then whole assembly can tilt like this about the F2, and in that particular case we will be having this plane correction mass we can able to obtain. So, you can able to see that when we are fulcruming here at F1, we can able to obtain the correction mass required at plane 2, and when we are fulcruming here F2, we can able to obtain the correction mass required at F1. Now, let us see how we can able to balance the rotor. So, if we have fulcrum, let us say at one of the point F1, and we want to obtain the correction mass at F2. So, this is a heat and trial method we are following. So, we will keep some trial mass in plane 2 at some orientation. So, let us say at 0 angle we will mark some angle there, some mass will keep some known mass, and then we will rotate the rotor at certain RPM. We will be having provision to measure the amplitude of the base. In this particular case, we will be having, we can able to measure how much this particular base is vibrating. So, that amplitude, let us say, is coming here. We will change the orientation of the mass at the plane 2 at different positions, and we will measure the amplitude and we will plot it. So, from this plot is we can able to see that when we are keeping the unbalance in this angular position, the amplitude of vibration is minimum. So, that means this is the correct location of the unbalance, trial unbalance we need to keep. So, once we have found out what is the angle at which in a rotor, so I am talking about a rotor angular position. So, let us say this is 0 angle, and so corresponding to this, if it is let us say 120 degree, so we need to have correction plane at here. So, this is 120 degree. Now, once we obtain this particular angular position, now we can able to change the magnitude of the trial mass and observe the magnitude in the same place at the same speed. All the measurements we are doing at the same speed, and we will plot for different trial masses how the variation of the amplitude is taking place, and from this wherever the minimum amplitude is there, that particular mass will be the correct mass, correction mass in plane 2. So, from this we got the angular position, and from this we got the magnitude of the unbalance. Now, we could able to get the correction mass in plane 2 by this heat and trial method. Now, in second case we will fulcrum here, and we will try to do the same experiment to find out the location and the magnitude of the correction mass required in plane 1. So, like that we can able to do balancing of this particular rotor using the heat and trial method. Summarize. Okay. So, in today's lecture we try to introduce a very common fault which is inherent in the rotor system, that is unbalance we introduce. Apart from that, we introduce that there are several other kind of fault, but most common is the unbalance, and this particular unbalanced rotor gives unnecessary forces onto the bearing, because the centrifugal force comes because of the unbalance, and that comes onto the bearing, and bearing fail because of this unbalanced force if this unbalanced force is of high magnitude. So, we need to balance this particular rotor not only at the stage of commissioning the rotor, but also whenever we are doing a major overhaul, we need to balance a rotor, and we need to check whether they are having acceptable limit of vibrations or not. And we already seen in the lecture that there are some standards which gives what should be the minimum tolerance or the tolerable amount of unbalance we can have in the rotor system, and it depends upon application to application. In subsequent lecture, we will try to go more deep into the various methods which are available for dynamic balancing of the rotor, which basically ensures the minimum number of measurement to be taken, and in the subsequent lecture we will see even the balancing of the flexible rotor.